Welcome back to Western Washington University. I am Aaron Clausen, and unfortunately I'm in front of the camera. Our good fortune is that Sean Basler is behind the camera and behind the project and is making all of the magic happen. So if you've been following us, last time we talked about floating point numbers and the exceptional cases in floating point numbers, and there should be a link somewhere down here if you want to go watch those videos and catch up. This week what we're going to talk about are structs and unions. These are C keywords. Most languages have something similar, but I'm going to stick with the C syntax. So our goal is to understand a structure, which is one of the simplest ways to put data types together to make a big composite structure, and what they're going to look like in memory. And I should warn you ahead of time, we're going to look at memory in two different ways, because typically we draw it, in my opinion, upside down. But let's start with things that are right side up. So if I have a struct point, and let's say it has an int x and an int y. Just fair warning, that semicolon is very important and often forgotten, especially when I write code. This creates a new type called struct point. It has an x in it and it has a y in it. They're both integers. And I'm just going to assume that integers are 32-bit numbers. If you're on different equipment, an integer may actually be 64. So if we look at memory, and this is the way I like to look at memory, with the little addresses up here and the big addresses down there. This is how I like to look at it. The rest of the industry turns this upside down. So if my point object is right here, let's say actually, this is why that semicolon is so important. This actually declares a variable called p of type struct point. I don't know why they did this. If p is actually right here in memory, this would be p.x, this is p.y. It does exactly what you'd expect. It puts the integer x first and the integer y right after it. It can be a little weird if these data types aren't the same size. For example, if rather than a 32-bit int, I made y a 64-bit long, and depending on your architecture, a long might be a long to get 64 bits. But let's just say this is a 64-bit long, and x is a 32-bit int. We get into this alignment issue. And generally what the compiler tries to do is put objects in memory that are size aligned. So if I'm x and I'm a 4-byte integer, whatever address x is going to be at is going to be aligned on a 4-byte boundary, so some multiple of 4. If y is an 8-byte object, like a long, it's going to be 8-byte aligned. So I actually can't do this and have a piece of y take up those two 4-byte chunks, because this isn't necessarily 4-byte aligned, or 8-byte aligned rather. Instead what we do is we insert some padding, and our piece of y gets shifted down 4 bytes. So if x is on a multiple of 4 and p is on a multiple of 8, this padding in here that isn't used pushes y into the right spot in memory. Now here's why I like this view of memory, is it follows the same order as we declare the variables of the structure. So this makes sense. It also follows because the littlest address in our text file is first, and the addresses of our characters get bigger as we go down. Usually we draw memory the other way around, in which case our p would start there. Our p.x is that. This is our padding, and this is p.y. This is why I feel like it's upside down. It is convenient because the smaller addresses are down here and they build their way up to the larger addresses, which is why it's the convention when we draw memory is to have little addresses down here and big addresses up there, to me it feels upside down because I'm used to the tactile. So that's a structure. This is our AND type. A point is both an X and it's a Y. The other data type we have is a union. I'm sorry, the other composite structure we've got is a union. This is actually a logical OR type. So rather than being both an integer X and a long Y, it's only one of those. And in memory, if our P is still starting in that byte of memory, P.X refers to that same 4-byte chunk. P.Y, however, refers to those 2 bytes. And notice that they overlap. The 4 bytes for X are 4 of the 8 bytes for Y. This is that OR. I can only fit an X or a Y. I can't fit both of them. And that's why our union is that logical OR type. So let's work through an example. You may be asking yourself, why do I need unions if I have structures and structures if I have unions? And as an example, I'm going to use license plates. So you may be surprised, but Western Washington University actually is in the state of Washington, just barely if you look at a map. And we have license plates, even up here in the frozen north. And if you look at the back of a car, a license plate is 3 letters followed by a 4-digit number. And if you look at a motorcycle, well, for starters, a license plate is much smaller, but I'm going to draw it so you can see it. It's usually a number, a letter, and a 3-digit number. Why they made this distinction, I don't know, because you can tell right away if it's a motorcycle or a car. But they have. So when if I'm writing software for the licensing department, I want to capture this type of, a vehicle either has a license plate that looks like this, or it has a license plate that looks like this. And I can do that by combining structures and unions. So let's start with the car type. It's a structure because it's both 3 letters and it's a number. So I would have a struct. I'm not going to actually name the data type, and I'll explain why in just a minute. But my structure for a car is going to be 3 characters. That takes care of that ABC. And it's going to be a 3-digit number. I'm sorry, it's going to be a 4-digit number. And I'm going to call that variable n. An integer has enough precision to capture a 4-digit number. And just like before, rather than naming the data type, I'm actually going to name the variable. And I'm going to call this variable car. If you're a list person, let me apologize now. So that's going to handle the license plate for automobiles, 3 letters and a 4-digit number. Let's do the motorcycle. Again, I'm not going to name the data type, but I am going to name the variable. So that is an int, I'm going to call it n1, a character that I'm going to call c, and another integer called n2. And this is going to take care of that 1-digit leading number. Yes, an integer is more than enough to store a single digit. My one and only character, and then my second integer that's a 4-digit number. Sorry, a 3-digit number. Again, an integer has plenty of space. And I'm going to call this a bike. Now the reason I haven't named these structures is I'm going to immediately put these into a larger data type. It's called a union. And that's going to capture this OR type of the license plate. The vehicle either is a car and has a car license plate, or it is a motorcycle and has a motorcycle license plate. Now, if we look at memory, what we'll see, in the case of a car, is those three 1-byte characters. So this is going to be my license plate dot L. So my L.C is going to be right here, and that's also where my license plate L starts. I need this one little byte of padding so that the integer L.N is 4-byte aligned. If it's an if it's a motorcycle, if it's a bike, my structure L is going to start at the same spot. My union L is going to start at the same spot. But this first 4 bytes, L.N1, is actually going to start where the character started for the car, followed by one character for the character in the license plate and 3 bytes of padding. And those 3 bytes of padding put L.N2 on a 4-byte boundary. So if we ask ourselves how big is a license plate, it's 3 4-byte chunks of memory, so 12 bytes, even though one of the nested structures is only 8 bytes. We take the larger of the two. Now, if you're more comfortable with a language like Java or C#, languages with class, languages with classes, you might say, I don't actually need the union types, I don't need the OR, because it already gets taken care of in the hierarchy I can define with a class and derived types. Well, that's exactly what a union is for. It's saying, I have a base type called license plate, and from that I've derived 2 types. A car, which has this structure, or a bike, which has this structure. But fundamentally, it's an OR type. A license plate is either this or it's that.